This is the pre-lab talk for experiment number 7, acids, bases, salts, and buffers. The main goal of this experiment is to make pH measurements of several different types of solutions and draw conclusions from these pH measurements. We're going to measure the pH of strong acids and weak acids, salt solutions, and buffered solutions. We're also going to practice dissociating ionic compounds into their constituent ions so that we can describe their pH nature. And we'll also briefly practice writing molecular and net ionic equations for Blab reactions. I use Blab for Bronsted-Lowry acid-base reactions or proton transfer reactions. Today we'll also use, of course, a new piece of equipment, the Vernier pH sensor, along with the Logger Pro software. In today's safety pause, we see that in this lab, there are going to be several acid and base samples that are mildly corrosive, since they have concentrations of 0.1 molar or less. We want to use care when handling them and wash our hands or skin if we come into contact with them. This lab also has us handling many different reagents. It is important that we label these reagents, handle them carefully, and avoid cross-contamination. Finally, to dispose of the waste for this experiment, we want to make sure that all acids are neutralized before being flushed down the drain with plenty of water. We'll do that by collecting all acid samples, adding NaOH until the solution is slightly basic, and then flushing the waste down the drain. We also want to make sure that we're wearing our safety goggles and flame-resistant lab coats and gloves when necessary. This is a 6-part experiment, and many things are going on during this experiment. So let's start by reviewing some concepts that will come up in this experiment. Let's first take a look at some definitions of some different types of solutions that we'll be measuring the pH of. The first is we want to remember the distinction between strong and weak acids. This distinction was made by Svante Arrhenius when he formed his ionic theory of solutions. Strong and weak here only deal with the percent that the compound is ionized when it's dissolved in water. Strong acids ionize completely in water. That is, all of the molecular acid is converted into H plus or H3O plus hydronium ions. A weak acid, on the other hand, only ionizes partially. Most weak acids ionize usually less than 5%. This is the only distinction between strong and weak acids for this course. Many times students mistake strong and weak with how dangerous the compound is. There are many weak acids, for example, hydrofluoric acid, that is an extremely dangerous compound due to the fact that the fluoride ion can actually leach calcium out of the bones if exposed to hydrofluoric acid. However, hydrofluoric acid is considered a weak acid due to the fact that it only partially ionizes in water. Another type of solution we'll be making in this lab are salt solutions. Technically, salts are ionic compounds formed during acid-base neutralization reactions. You might have learned in lecture that salts can either be acidic, basic, or neutral based on what ions they make them up. We'll be exploring this a bit in this lab. The third type of solution that we'll be measuring are buffered solutions. Buffered solutions are solutions that contain a significant amount of a weak acid in its conjugate base. The effect of having both of these substances in the same solution is that The solution will resist drastic changes in pH even when small amounts of a strong acid or strong base are added to them. Okay, so now that we have some definitions down, let's take a look at some important skills to have for this lab. In the next slide, we'll talk about pH calculations and the percent ionization, but that's an important skill to have as well. You might be asked to write net ionic equations for several different types of proton transfer reactions. The first type is ionization. This is a reaction between a weak acid or weak base that does not have a charge with water to form the conjugate acid or base and H3O plus or OH minus. Most of our solutions for this experiment will be acidic solutions, and therefore will undergo acid ionization if the acid is a weak acid. The next type of reaction is hydrolysis. Hydrolysis is similar to ionization, except you're starting with an ion rather than a neutral compound. Protons are transferred between the ion and water to form H3O plus and OH minus, as shown on the right. Note that BH plus is an acidic ion and A minus is a basic ion. Finally, in a neutralization reaction, acids are reacted with usually a strong base to form the conjugate species and water. For example, the red reaction under neutralization shows that the acid HA is reacted with OH minus coming from a strong base to form the conjugate base of the acid and water. A similar reaction happens between the weak base and H3O plus to form BH plus and water. Neutralization reactions occur typically when adding strong acid or base to a buffered solution. Now let's take a closer look at the skills of pH calculations and calculating a percent ionization. The pH calculations that you're going to do today are pretty simple. You'll be measuring a pH using the pH sensor, and you'll be asked to calculate the H plus or H3O plus concentration. Those are one and the same. To calculate the hydronium ion concentration from the pH, you'll raise 10 to the negative pH. That is, the H3O plus concentration is equal to 10 to the minus pH. You will also be asked to calculate a percent ionization for weak acids. As mentioned, many weak acids have a percent ionization that's less than 5%. To calculate the percent ionization, you take the H3O plus concentration and divide it by the original concentration of the acid. In this lab, most of the acids have a 0.1 molar concentration, and then multiply by 100%. If you're asked instead for the fraction of the acid that's ionized, you simply don't multiply by 100. Therefore, you get a fraction out of 1. Let's take a look at some procedural points now. Many of the points here are about using the new piece of equipment, the pH sensor. As you can see from the picture, the pH sensor is an electrode that is stored in a test solution. We have the pH sensor stored in an upright position in a cabinet in the lab rooms. It is important that pH sensors are always stored in their test solution. During the experiment, it's also important that we don't let the pH sensors dry out. Therefore, we will usually store the sensor in either the test solution or pH 7 buffer, and in other cases in water. We also want to make sure that the sensor is rinsed thoroughly between measurements, simply by swirling it in some water. pH sensors are electrochemical cells that do need to be calibrated, since they're converting a measured voltage into our pH measurement, something you might take a look at when you talk about electrochemistry in lecture. pH sensors undergo a 2-point calibration, which is described in your lab manual. We'll first calibrate the sensor at pH 7 using a pH 7 buffer, and then at pH 4 using a pH 4 buffer. We calibrate at both neutral and acidic for this experiment, since we'll be mostly working and measuring pHs in the acidic range. If you were doing an experiment where you were mostly measuring solutions in the basic range, you might want to calibrate with pH 10 instead of pH 4 buffer. When we make pH measurements, it's important that we keep the solution stirring. In this experiment, we'll stir with a magnetic stir bar and stir plate. We also want to make sure that the sensor is fully immersed in the solution. For this experiment, we'll be doing that by filling our beaker about halfway and immersing the sensor in the solution. Finally, we let this reading on the screen stabilize, and then we can record the pH. Note that the pH sensor is extremely sensitive around neutral pH, somewhere between a pH of 6.7 and 7.3. And it might take a little longer to stabilize. Another thing to note is that if your pH sensor is having a difficult time stabilizing, it might be necessary to recalibrate the sensor. It is not uncommon to calibrate a sensor twice during a single experiment. Another important point about this experiment is, since we're working with many solutions and many compounds, we want to make sure that everything is well labeled. You can easily label your solutions by writing on the lab benches with chalk. This is a method that I've been using while recording all the labs this summer. Another important thing is to make sure that the solid compounds do not become contaminated. If you notice that any compound is contaminated in a chemistry lab, you should report it to your instructor immediately so that the problem does not spread to other students. Another important thing about this experiment that you might not get to experience close up is the trial and error part of neutralizing our distilled water samples, which you'll find are usually a little bit acidic. We'll be adding small amounts of NaOH or HCl to our distilled water samples to get the pH in the neutral range, between 6.7 and 7.3. This does take trial and error, and although I'll be doing it probably faster than many students would, it still does take some patience. So bear with me. Okay, hope you have fun watching the video. It's my first effort in picture-in-picture.